Okay, so this video is going to be about uniform fields. Now in the last video we talked about electric fields and how to draw them, what they were, but here instead of having a single point in space, you're going to have something that looks like this. So this is like an infinite plane. By infinite I mean it goes on forever. So just as last time, if this infinite plane is positive, it means that the electric field that it creates is going away from it. Now, if it were negative, the electric field would be pointing towards it. To find the electric field, we do sigma divided by 2 epsilon naught. Because we're not given the charge of this entire plane, here we're just given sigma, which is the charge density, the area charge density. The area charge density is how many coulombs there are per meter squared. So if I were to take a meter squared out of this plane, let's say it's this big, I were to be asked, how much charge is in that meter squared? And here we can say that there is 1 coulomb per meter squared. And we're going to divide sigma by 2 epsilon naught, where epsilon naught is the permeativity of free space, but what you really need to know is its value, which is 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. Now, why do we need to know this and how do we use it? Here we have 3 planes. We have A, B, and C. For each of them, I'm giving you sigma, which is the area charge density. For A, there are 10 nanocoulombs per meter squared. So in every meter squared of this A, there are 10 nanocoulombs. For B, it has an area charge density of negative 50 nanocoulombs per meter squared. So that means it is negatively charged. And C has an area charge density of 10 nanocoulombs per meter squared. I also give you this information here. I say that the distance between A and B is 1 centimeter, and between B and C is 3 centimeters. Now you actually don't need to know that, and it's not going to help you at all, because remember this equation? We are just taking into account sigma and epsilon naught. Epsilon naught we already know, so the only value that we need to have is sigma. Now the question here is asking, if I have my star on the left side of all of these planes, and I have a diamond between B and C, what is the electric field felt by the star, and what is the electric field felt by the diamond? So each of these planes is creating their own electric field. The green ones have their electric fields that are pointing away from them. So here I have A, it's pointing to the left and it's pointing to the right. For B, I have both of them pointing towards it from either side, just like we had with our point charges. And then I have C, which again, because it's positive, it is having the electric field pointing away from it, just like we saw here, because when it's positive, the field is being pointed away. To find the electric field on the star, we just have to add up all of the electric fields it's feeling by A, B, and C. So A, it's also A is going to be pushing the star to the left, because this electric field is pointing away from it, so the star is being pushed to the left. Now B, it's the opposite, because the field is pointing towards the plane, meaning B is pushing the star to the right. And then C has its field pointing away from it, so it's pushing the star to the left as well. We can see that here. So we have C and A, their fields are pushing the star to the left, and we have B, which is pushing the star to the right. To calculate the electric field of A, B, and C, we just use our equation. EA is equal to sigma A divided by 2 epsilon naught, and that is in the negative I hat direction. For EB, it's sigma B over 2 epsilon naught, and that is going in the positive I hat direction. Now we have EC, which is sigma C divided by 2 epsilon naught. Now to find out the total electric field being felt by the star, we're adding them all up together, so we have negative A plus negative C plus B. Now, it'd be really cool if you were to do this and you were to take all of these values, so these are our sigmas, change them into coulombs, divide them by 2 epsilon naught, and then add them all up together, and that would be your resulting field. Now we do a similar thing with our diamond, but here the diamond is feeling the field a little bit differently. For A, the field is going away from the plane, so it's going to be pushing the diamond to the right. For C, it's going to be pushing the diamond to the left. But here, A and C are equal magnitudes. So if A is pushing the diamond to the right with the same force that C is pushing the diamond to the left, well, those two cancel out and don't do anything. But now for B, it's as though it is pushing the diamond to the left because the electric field is moving towards the plane. So actually, there's only one equation that you need to do. You need to find the electric field of B. So to do that, we take sigma B divided by 2 epsilon naught. And it is going to be in the negative I hat direction. Now there's one last thing here. So when you have two of these planes and they're parallel to one another, so here we have positive on one side and negative on the other side, there's going to be an electric field between them. And that electric field is going to go from the positive to the negative plane. Now to calculate that, you need this equation, and it is sigma, the linear charge density, divided by epsilon naught.